Hello, welcome to Marine Gurukul video series. In this ship stability 1 video, we shall take you through the concept of density, relative density, pressure, thrust, and the law of flotation only to the extent as required for our purpose. Density of a substance is its mass per unit volume. In SI units, the mass is expressed in kg and volume in cubic meter. So the SI units of density are kg per cubic meter. However, in ship stability, since large masses are involved, so mass is taken in tons and volume in cubic meters. Thus, in ship stability, the unit of density used is tons per cubic meter. As the mass of 1 cubic meter of fresh water is 1 ton, therefore the density of fresh water is 1 ton per cubic meter. Relative density of a substance is the ratio of mass of a certain volume of that substance to the mass of same volume of fresh water. That means we take the same volume of the substance and same volume of fresh water, we measure their masses, and the ratio of the masses then becomes the relative density of that particular substance. If we consider the volume to be, say, 1 cubic meter, then relative density shall be equal to mass of the substance in 1 cubic meter of the volume, the mass of fresh water in 1 cubic meter of the volume. And if these masses are taken in tons, then the numerator here becomes density of the substance when expressed in tons per cubic meter, and the denominator becomes the density of the fresh water expressed in tons per cubic meter, which we have already said that the density of fresh water when expressed in tons per cubic meter is 1 ton per cubic meter. And what do we see here then? These units get cancelled out, and we see that the relative density of the substance is numerically equal to the density of that substance when it is expressed in tons per cubic meter. So relative density of a substance, its value is exactly the same as its density when the density is expressed in tons per cubic meter. So please pay attention, it will be equal only if the density is expressed in tons per cubic meter. RD being a ratio of masses, obviously then does not have any units, so relative density is a unitless number. RD of a substance, as earlier said, is numerically equal to its density expressed in tons per cubic meter. In ship stability, we shall consider the following values of density and relative density. If seawater is given, its density shall be taken as 1.025 tons per cubic meter, and obviously then its relative density shall be 1.025, numerically equal to the density expressed in tons per cubic meter. If the water in question is fresh water, its density shall be taken as 1 ton per cubic meter. Relative density obviously then would be 1. If the water in question is dock water, it shall be any water of any density other than sea water and fresh water. If in ship stability the density of the water is not stated, then by default the water shall be construed to be seawater of density 1.025 tons per cubic meter or relative density 1.025. Let's take a numerical to better understand what we have just discussed. A cylindrical tank of radius 1.1 meter is 4 meters high. It has an ullage pipe of height 0.5 meters above the tank top. The tank contains fuel oil of RD 0.95 to an ullage of 1.4 meters. Calculate the mass of the oil contained in the tank. Also state the sounding of the tank. We have the cylindrical tank coming up in the diagram. The radius of the cylindrical tank is given in the question as 1.1 meters. The height of the tank is given as 4 meters. Above the top of the tank, we have an ullage pipe of height 0.5 meters. So that's the ullage pipe of height 0.5 meters. So the depth of the tank from top of the ullage pipe obviously becomes 4.5 meters. This tank contains oil to an ullage of 1.4 meters. Ullage is the height or the depth of the free space inside the tank. That means it's the height from the top of the ullage pipe to the surface of the liquid in the tank. That means if the ullage is 1.4 meters, if we go down by 1.4 meters from top of the ullage pipe, we should be reaching the top of the liquid. That means the surface of the liquid. That means liquid surface shall be somewhere in this line, and that is where we have the oil in the tank to an ullage of 1.4 meters. The way ullage is the depth of the free space in the tank, the depth of the liquid in the tank is referred to as sounding. So obviously sounding will be this depth plus the ullage shall constitute the total depth of the tank from top of the ullage pipe. So we have the total depth of the tank as 4.5 meters. We have the ullage as 1.4 meters. This means the sounding, which shall be this depth, will be equal to 4.5 minus 1.4, that is equal to 3.1 meters. So the ullage is 1.4 meters, the sounding is 3.1 meter. To get the mass of this oil, we need to calculate its volume, and that means we need to calculate the volume of the cylindrical oil of sounding 3.1 meter. Volume of the oil in the tank is area of the base multiplied by sounding of the oil. Area of the base shall be pi r square. When we put these values, we get the volume of the oil to be 11.789 cubic meters. We also know density is equal to mass upon volume, or mass is equal to volume into density. Volume we have just calculated. The density of the oil, we are given the RD in the question, and we already know that RD is equal to the density when density is expressed in tons per cubic meter. So the density of the oil is 0.95 tons per cubic meter. This gives us the mass of oil to be 11.199 tons. We know in physics, pressure at any point is the force per unit area. Accordingly, the SI units of pressure happen to be Newton, the unit of force, per square meter, the unit of area. As regards ship stability, we limit our scope to pressure exerted by column of water at any point below its surface or column of any liquid below its surface. The pressure due to column of any liquid at a point below its surface, also we know from physics, is given by H rho g, where H is the depth of the point below the surface of the liquid, rho is the density of the liquid, and g is the acceleration due to gravity. However, again, ship stability deals with the stability of the ships floating at the surface of the earth, where acceleration due to gravity practically remains constant. I said practically remains constant, minor variations are being ignored. So this G, because it practically remains constant and is part of every calculation of the pressure, so is intentionally kept aside. It's not neglected, it's not forgotten, it's just kept aside for the sake of easy calculations. So if we keep the G aside, then as far as ship stability is concerned, pressure becomes depth of the point below the liquid surface in meters multiplied by the density of the liquid, we know, which we take in tons per cubic meter. So the pressure shall be the product of depth of the point below the liquid surface multiplied by its density, And if we use these units of meter and tons per cubic meter, we get the unit of pressure in ship stability as tons per meter square. Thrust is the force exerted on a surface. That means total force experienced by the surface is referred to as thrust. As regards ship stability, we limit our scope to thrust, that is the force exerted by the liquid or the water on the immersed area or the immersed surface. Thrust on the immersed surface shall be sum total of pressure experienced all over the surface and is obtained by product of pressure at the geometric center of the immersed area. So it's the pressure at the geometric center of the immersed area multiplied by the immersed area, and that shall give us the thrust. We have just done before this the pressure. What will be the pressure at the geometric center of the immersed area? It shall be the depth of the geometric center of the immersed area below the liquid level multiplied by the density of the liquid. So these two terms here shall give us the pressure at the GC multiplied by the immersed area. So thrust can be obtained by getting the pressure at the GC of the immersed area. That pressure shall be equal to the depth of the GC of the immersed area below the liquid surface multiplied by the density of the liquid. And when this pressure at the GC is multiplied by the immersed area, that shall give us the thrust. Now, when we put the units of depth as meters, density as tons per cubic meter, and area as meter square, we get the unit of thrust as tons. So unit of thrust in ship stability shall be tons. Let us now take a question. A box-shaped vessel 50 meters long, 10-meter wide is floating at an even keel draft of 4 meters in sea water. It has a starboard side double bottom tank, 15-meter long, 10-meter wide and 2 meters high. The DB is full of fresh water to a head of 7 meters. Calculate A. Thrust experienced by the ship's hull because of the outside water. Also state the direction in which this thrust shall be acting. B. Resultant thrust acting on the starboard side of the DB tank. The thrust experienced by the ship's hull because of the outside water shall be the thrust experienced by the keel, thrust experienced by the two sides, immersed part of the two sides, and the immersed part of the two ends of the box-shaped vessel. So here is the box-shaped vessel of length 50 meters, breadth 10 meters, floating at a water line with a draft of 4 meters. You can see it here in the diagram. Let's calculate the thrust on the keel plating. So in the diagram, let's identify the keel plating. I'm sure you'll agree that this one shaded out here is the keel plating, which is rectangular in shape, of length 50 meters, breadth 10 meters. The thrust on the keel plating shall be equal to the pressure at the GC of the keel multiplied by the area of the keel. And what shall be the pressure at the GC of the keel? It shall be the depth of the GC below the liquid surface multiplied by the density of the water, and obviously lastly multiplied by the keel area. This keel is rectangular in shape. Its geometric center shall be at the intersection of diagonals. The depth of the GC shall be equal to the draft. So we put the values here. Depth of the GC is 4 meters multiplied by density of seawater, which is exerting the pressure, multiplied by the area of the keel, that is 50 meters long, 10 meters wide, and that gives us thrust on the keel as 2050 tons acting upwards, or you can say inwards. Now we consider the thrust on the immersed part of the two sides. Let's first shade those two immersed areas. I'm sure you'll agree that the areas highlighted by the vertical green lines are the immersed areas on port and starboard sides. Both areas are identical, so the thrust on both shall be calculated by doubling up the thrust calculated on one area. So this shall be equal to twice into pressure at the GC of the immersed area multiplied by the immersed area. Why twice? Because what you'll get in the bracket would be a thrust only on one side and doubled up to account for the other side. This shall be the depth of the GC of the immersed area into density of the water into immersed area. Now this immersed area you can see is rectangle whose length is 50 meters, height is 4 meters. Its geometric center shall be at the intersection of diagonals. The depth of the geometric center shall be 2 meters from the liquid level. So we put these values here. Depth of the GC is 2 meters. Density of the water is seawater multiplied by the area of the immersed side on one either port or starboard. And when we double it up by multiplying by 2, we shall get the thrust acting on both the sides. So the thrust acting on the two sides is 820 tons again inwards. Now what are left are the two immersed surfaces at the ends. So let's identify those surfaces. This is the immersed surface at one end and similar would be the immersed surface at the other end. Now these two immersed surfaces also happen to be rectangle of length or breadth 10 meters and height 4 meters. They are identical surfaces, so we shall calculate the thrust on one surface and double it up. So this shall be equal to 2 into pressure at the GC of the immersed area multiplied by immersed area. The GC of this immersed area shall be again at the intersection of diagonals. So it shall be at half the draft from liquid surface. So we put these values and we get the thrust on the two sides accounting for 164 tons again acting inwards. The total thrust experienced by the entire immersed hull shall be sum total of thrust on the keel, thrust on the two sides and the thrust on the two ends, and the total thrust then becomes 3034 tons acting inwards. The thrust experienced on the starboard side of the DB shall be the resultant of the outward thrust because of fresh water inside the tank and inward thrust because of the seawater outside the ship. Here we have the box-shaped vessel, 50 meters long, 10 meters wide, floating at a draft of 4 meters. Now let's represent the DB, which is 15 meter long, 10 meter wide and 2 meters high. So this represents the blue shaded boundaries here represent the boundaries of the DB. This DB is 2 meters high. It's full of fresh water. This is 10 meters in width and 15 meters in length here. So DB, the starboard side of the DB shall be 15 meters long and 2 meters high. The DB contains fresh water to a head of 7 meters. What does this head of 7 meters mean is that there is fresh water or the tank content inside the sounding pipe to a height of 7 meters above the top of the tank. So here is the sounding pipe and here is what represents the head of fresh water. This is 7 meters above the top of the tank. So if this head is 7 meters and height of the tank itself is 2 meters, then obviously the sounding will become 9 meters. Sounding of the DB becomes 9 meters. Now let us identify the geometric center of the starboard side. This is a rectangular side, 15 meters long, 2 meters high. Its geometric center shall again be the intersection of diagonals and it shall be obviously 1 meter above the keel because the height of the DB is 2 meters. So this geometric center shall be 1 meter above the keel. So distance of the GC of the DB starboard side from keel is 1 meter. Now let's calculate the outward thrust on the DB starboard side due to this tank content of fresh water to a head of 7 meters. This shall be equal to the pressure at the GC of the starboard side. Where is the GC of the starboard side? It's here. Due to the fresh water inside the tank, multiplied by the area of the starboard side. What shall be the pressure at the GC? It shall be the depth of the GC from the surface of the fresh water multiplied by density of the fresh water multiplied by the area of the starboard side. Now the depth of the sounding of the fresh water is 9 meters as already explained. The height of the GC above the keel is 1 meter. Therefore, the depth of the GC from the surface of the fresh water in the sounding pipe becomes 8 meters. It's 9 minus 1. And 9 minus 1 basically becomes the height of the liquid surface or the depth of the GC below the liquid surface. Density of the tank content is 1. Why? Because it's fresh water. And the area of the starboard side is 15 into 2. That gives us outward thrust of 240 tons acting on the starboard side of the DB because of fresh water to a head of 7 meters. Now we calculate the inward thrust on the DB starboard side because of the outside seawater. It shall be the pressure exerted by seawater at the GC of the starboard side multiplied by the area of the starboard side of the DB. Pressure at the GC shall be equal to the depth of the GC below the surface of the sea multiplied by the density of the seawater multiplied by the area of the starboard side of the DB. Now, where is the sea surface here? It's here because of the 4 meters draft. What is the height of the GC from keel? It's 1 meter. So what is the depth of the GC below the sea surface? It becomes 4 minus 1, that is 3. And that becomes 4 minus 1, 3 meters is the depth of the GC from the sea surface, multiplied by the density of the seawater, multiplied by the area of the starboard side, and that gives us inward thrust of 92.25 because of the outside seawater. So the starboard side of the double bottom tank is experiencing 240 tons of outward thrust and 92.25 tons of inward thrust. So the resultant thrust on this starboard side shall be algebraic sum of these two, which becomes 147.75 tons outwards. Why? Because the outward is greater than the inward. So it's 240 outwards minus 92.25 tons inwards, leaving the resultant thrust on the starboard side as 147.75 tons outwards. Law of flotation. The ship floats as per law of flotation, and this law of flotation is a corollary of Archimedes' principle. Whenever a body is immersed in a liquid, it experiences an upthrust which is equal to the weight of the liquid displaced. The upthrust is also referred to as force of buoyancy. As the body immerses more and more because of its weight, the volume of the liquid displaced also increases, thus increasing the force of buoyancy. At any level of immersion of the body, when the buoyancy becomes equal to the weight of the body, the two forces balance each other. At this stage, the body floats. From generic law of flotation, now we specifically talk about flotation of the ships. The watertight or the submerged underwater hull of the ship displaces seawater that provides buoyancy. This buoyancy is then equal to the weight of the water displaced, and this weight of the water displaced is equal to the volume of water displaced multiplied by the density of the water. And since this volume of water displaced is responsible for providing buoyancy, it is also referred to as volume of buoyancy. Therefore, we can say buoyancy is equal to the volume of buoyancy multiplied by density of the water in which the ship is floating. In case of vessels with intact hull, volume of buoyancy is obviously the same as the underwater volume of the vessel. So in such cases, buoyancy is equal to underwater volume of the ship multiplied by the density of the water. Why? Because the underwater volume of the ship is same as the volume of buoyancy as long as the vessel is intact. Since the weight of the ship is determined by the weight of the water displaced, the weight of the ship is referred to as displacement. The units of displacement of ship is tons. Let's try and solve this question. A barge consists of identical triangular cross section all along its length. The barge is 40-meter long, 12-meter high, and 10-meter wide at the deck. It displaces 150 tons in water of RD 1.005. Calculate its draft. Here is the cross-sectional area of the barge. The barge is 40-meter long, 10-meter wide at the deck, 12 meters in height. That means depth from keel to the deck is 12 meters. Let us say this barge is floating at this water line out here at a draft of small d. This small triangle here represents the underwater cross-sectional area of the barge. Now let us say this breadth of the barge at the water line is small b. We know that this big triangle, which represents the cross-sectional area of the barge, and this small triangle, which represents the underwater cross-sectional area, are similar triangles. Therefore, their heights and the corresponding sides are in the same ratio. So using the property of similar triangles, this small d, which is the height of the small triangle, divided by the height of the bigger triangle, 12 meters, shall be equal to the ratio of these two sides, that is the small b by 10. So by similar triangles, d by 12 is equal to b by 10, which gives us the relationship between draft and small b. The draft is equal to 1.2 times small b, where b is the breadth at the water line. So this expression gives us a relationship between d and b. Now we know that the displacement of the barge is equal to the underwater volume of the barge multiplied by the density of the water. The underwater volume of the barge shall be its underwater cross-sectional area multiplied by the length of the barge and multiplied by the density of the water. So the underwater cross-sectional area, we know its triangle, it shall be half base into height. Base is small b, height shall be d. So here in the brackets is the underwater cross-sectional area, which when multiplied by the length gives us underwater volume, which when multiplied by density shall give us the displacement of the barge. So now we have the displacement of the barge is given to us as 150 tons. We put the values of d as 1.2 b here and value of length and density, which are also known to us. When we put all these values, we get expression in small b, and when we solve for it, we get the small b, which is the breadth at the water line, as 2.494 meters. And we already have a relationship between d and b, d being 1.2 times b, the draft becomes 2.993 meters. Therefore, the draft of the barge is 2.993 meters. Let's take one more question before closing the video. A box-shaped vessel, 100-meter long, 20-meter wide, floats in seawater at a draft of 5 meters. Calculate her draft if she moves in the same condition to water of RD 1.003. So first we take this vessel in seawater. This is the box-shaped vessel that we have. It's 100-meter long, 20 meters wide, floating at a draft of 5 meters. So we can get to know the underwater volume, which can give us the displacement of the vessel. The displacement of the vessel shall be equal to the underwater volume in seawater multiplied by density of the seawater. Underwater volume in this case, I'm sure we are now comfortable, shall be this cross-sectional underwater area, that is the breadth multiplied by the draft and then multiplied by the length. It's cuboidal, length into breadth into draft, and multiplied by density of seawater 1.025. When we put these values, that gives us the displacement of the vessel as 10,250 tons. So by solving her condition in seawater, we have been able to get the displacement of this vessel. Now with the same displacement, this vessel goes to water of RD 1.003. The vessel is in now dock water with the same displacement. Obviously her draft would change. Let's say now her draft is D. This draft D is in dock water of RD 1.003. We can calculate the underwater volume of the vessel in the dock water, and when that underwater volume is multiplied by the density of the dock water shall give us the displacement, and we already know the displacement. The displacement shall be equal to underwater volume in the dock water multiplied by the density of the dock water. It shall be equal to length into breadth into draft into density of the dock water, and that since the vessel has moved with the same displacement, so the displacement is now known, 10,250. When we put the value of length and breadth in this expression and the density of the dock water, the expression looks like this, and when it is solved, we get the value of D, that is the draft, as 5.110 meters. So the same vessel, when she moves from seawater to dock water, her draft shall change from 5 meters to 5.110 meters. Now we come to end of Ship Stability 1 video. Please do subscribe to our channel in case you would like to get notification for the other volumes as they get released. If you have any feedback, write to us on marinegurukul@gmail.com. Thank you very much for watching Marine Gurukul video series. Thank you once again.